So our next speaker is Hayden So. He's an associate professor at the University of Hong Kong, and he's going to be talking to us about hardware acceleration of neural network pruning through co-design of algorithms and architectures.
Yes. Okay, good morning, everybody. My name is Hayden So from University of Hong Kong. Today, I'm going to talk about our work on DPACS, which is an accelerator for performing dynamic neural network pruning. This work is done mostly by my student Yizhao and Baoheng. They are both sitting in the audience today, and as well as my collaborator Xiaojuan, who is expert in computer vision. So dynamic pruning, so what is that? Network pruning, I believe many of us are familiar with. Essentially, is a way for us to reduce the redundancy in or leverage the redundancy in the neural network. So when our network is pruned and becomes linear and smaller, the idea, or at least the hope, is that it's going to run faster. So in static pruning, that's the typical way of performing network pruning. What we have is we start with a large model. We have a whole bunch of training data come in, retrain the network, and then we look for connections or weights that are not as significant as other, and we try to remove them and come up with a new pruned network, a linear version of the network. We'll put the linear version of the network online during runtime, and then we are going to run our runtime inference on the pruned network. But as you can see, because obviously for just like any other neural network algorithm, we'll be training with our training set, and during runtime, we have a different ostrich and boats coming in, so the accuracy can suffer. What dynamic pruning is doing, however, is similar but quite different. We still need to retrain, but during offline training, we still use the same set of training data, but instead of training a network, we are now training a new addition to the network, which we call is a pruning unit. We basically train the pruning unit. What happened is then during runtime, when we have our actual data, inference data coming in, say if there's an ostrich, a boat, or an eagle coming in, it will go first through this pruning unit, which is dynamically during runtime determines which of the connections in the original network should be eliminated and pruned. And as a result, you can see during runtime, essentially we'll be having different catered network for different inputs. And as experiment will show you, dynamic pruning usually tends to give you better performance, which is kind of intuitive because you now have a network that is tuned to your input. Now, it all sounds very good, except when you sit down and think about it, it's actually not quite easy to achieve. And in fact, most existing algorithms, when you start implementing them, you will see a slowdown instead of speed up. Because during training, when we design an algorithm for dynamic pruning, flops, the number of operations that we need in the network, is usually a proxy for us to train our network. However, in this community, we understand that when you reduce the number of flops, it not automatically means that you will actually be having any system speed up. Sorry. First of all, of course, you will have your runtime overhead, which is kind of obvious, but it can be large because we are now saying that for each input coming to our network, we will have to first examine the input before we will actually inference on the input. So we are doing double the work. So if you're not smart about the overhead can overwhelm you. Two is because now we are doing pruning dynamically during runtime. That would mean that once we prune the network, it becomes very sparse, but the sparsity is unknown during compile time. So that means we have to deal with this dynamic sparsity, and which is not a trivial thing in hardware. Finally, like I said earlier, the more you prune in terms of compute, the more you are going to hurt your I/O to compute ratio. And as a result, very soon you'll find yourself in an I/O bounded era. So you'll be pruning computation. You think you'll be getting faster, but you're now getting bounded by I/O. So How do we solve this problem? In DPACS, essentially, we have an algorithm that performs dynamic pruning on both the spatial dimension as well as the channel dimensions. We'll talk about that. And the key message from DPACS is that when you want to do something that is so tricky like dynamic pruning, you really need to do a careful algorithm hardware co-design. So in the following slides, I'll walk you through some of the details on what we have done to co-optimize the algorithm as well as the hardware to ensure at the end we will have a dynamic pruning system that has good accuracy, but at the same time give you some real speed up. So in a nutshell, DPACS looks like this. We basically works on a residue block on the ResNet. So that will be our starting point. Everything happens within the block. If you have a larger network or any network that builds on top of this residue block, you are fine to do so. Then we develop a relatively simple pruning mechanism using a mask. We have both a spatial mask as well as a channel mask. Both of them are relatively simple. Then we specifically chose to share these masks within the layers within the residue block. So all the blocks will be seeing the same same mask that will have, first of all, the effect of reduced overhead. And in fact, when we get to the hardware implementation, it will actually be helpful. Then we develop a elastic data flow engine within the residue block, so we can deal with the dynamic sparsity that are generated from pruning. Finally, a small but important trick is that we actually also carefully position where we actually performs our channel mask computations to reduce the amount of I/O. Hardware, so it's algorithm. Then how about hardware? The hardware mimics sort of our residue block. Our accelerator essentially look at the entire residue block and try to optimize within it. Now, getting to this hardware, you will start to see where the simple spatial mask will be useful. It's really simple. We use a conv 1x1 layer for inspecting our input. Essentially, that means when we have our input coming in, we are just going to look at 1 pixel of it. And from there, we will be able to give some hints to the rest of the network to see how important that particular pixel is. That's why it's a mask. For channel pruning is slightly more complicated. We actually have to do a pooling layer as well as a fully connected layer on the output. But we do it in a special way. First of all, we do it in the output, not in the input. We'll come back to that point. 2 is that we only work on sparse inputs for this particular channel mask. Finally, this is what I was talking about. Within that block, we actually carefully design the pipeline so we can actually parallelize the 3 layers within the residue block with an elastic buffer, and that will help us with our performance. So let's go through that very quickly so you can have a taste of what that is. If you look inside a residue block, for example, in a ResNet 50, what you see is 3 layers, a conv 1x1 layer, followed by a conv 3x3 layer, and then a final conv 1x1 layer. So mathematically, in the terms of algorithm, what you need to do is to, first of all, in the first conv 1x1 layer, you go through every single features, every single activation and input. That produce data to your next layer, your conv 3x3, and then on the conv 3x3, you have these windowing operations that produce the result for last conv 1x1. Now, how do we pipeline that? Because we really don't want to do it 1 by 1. So this is how we did it. First of all, like I said earlier, we have a shared mask that was by design. So in this case, we show what a mask would be like. This is a spatial mask that we are showing. The orange color means that we are interested in this pixel. White colors means that we are not interested in that pixels. Now, if you go through the operations of the elastic buffer, that's what you will see. Let's say we now start with our top left pixel here, position 0, 0. We perform our conv 1x1 and finally get our answers, which are to be passed to our next layer. When you pass the output of the 1x1 layer to the next layer, it will go to the same position 0, 0. We are done. We push. What we did is we push this index 0, 0 into this elastic buffer, so we know now at the head of this 5.0 is going to be 0, 0. What happened to the next pixel? We perform the next pixels, 0, 3. Nothing happens. The same. We perform the same conf one by one, get the result, put it into buffer, and push the index to the FIFO. Still nothing happened too interesting. Now, the next one. So we are done with the first pixels. The second pixels, remember, is sparse. We skip all the white space. Then we get to the next pixel location one by one. We similarly perform one by one conf. Then we also get the output into the buffer, but now something different. If you look at now on the 3x3 layer, you would notice that this 3x3 windows corresponds to the original 0, 0 is now ready by looking at just the 3x3 area. So all of a sudden, we can now say that we have all the data needed for this particular pixels, which is our first input pixels for the last layer. So in that sense, then we can now pop 0, 0, because we are now finally at the point that we can compute to this 0, 0. And we're using the data in the buffer, while at the same time in parallel, we of course will be still pushing our 1, 1 here. Do one more example. Next, we deal with the next pixels, which will be right here, going to 2, 1, get to this particular point. Now, some details in the paper tells you how you do the math. But if you do the math, that fact that you're pushing 2, 1 into the system will tell you now you are ready to perform 0, 3 computation. So that's how the pipeline will work. You continue, 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 continue. And at the end, you will find that by just looking at the FIFO index, we are able to control the flow of data through these 3 layers without really waiting for anything in between. And we can truly leverage the pixel sparsity therein. Channel pruning, I mentioned we also did some tricks there. One of the things is we computed at the output of the block. Why do we want to do that? Now, to understand that, you have to look at this connection between 2 layers. Because after all, the output of one layer is the input of the next layer. But remember, we are going to prune our input. So intuition will tell you that if we are going to prune that input, why do I want to save the output? So that's sort of the fundamental idea. We do it on the channel dimension. So this quickly show, for example, in this output features, this slice all belongs to one particular weight, and that will end up in particular area of the weight. So we know that we actually will be able to avoid saving and loading extra weight. We also do it in a coarse grain fashion to save some more computation. So very quickly, to summarize, does it work? The answer is yes. We can have up to 4x speed up with reasonable accuracy, because obviously accuracy degrades when you prune more data. But the accuracy is actually on par. We are still sitting at the same parameter front of the state of the art. In terms of overhead, how do we do? We are actually doing way better than other systems, and we are finally sitting at the 1:1 ratio. So in short, is I briefly tells you that if done right, dynamic pruning is actually a very interesting technique for improving the speed of inference. But to do it right, you really have to consider both hardware and software to do. Thank you.